We're going to finish off combinatorics by looking at this thing called the pigeonhole principle. And it's a fairly basic idea. Simply this: if you've got n plus 1 or more objects, and you've got to put them into n holes or containers, then there must be at least one hole that has 2 or more objects. That's pretty much the pigeonhole principle. It's an interesting little proof, this one. We're going to prove it. Let K be the maximum number of objects you can put in n holes without having any more than one in a hole. So we want to prove that K is less than n plus 1. That's what we want to prove. Okay, here's the proof. I'm actually going to assume the opposite. I'm going to do it by contradiction. I'm going to assume K is actually greater than or equal to n plus 1. Now, the maximum number of objects equals n. That's when each hole has one object. So therefore, K must be less than or equal to n. There's my contradiction straight away. Because how's it going to be greater than or equal to n plus 1, but also less than or equal to n? That's impossible. So therefore, it can't be true that K is greater than or equal to n plus 1. So yes, K is less than n plus 1. To be honest, I don't know if I'm happy with that proof, but anyway. It's a very simple idea, and intuitively we can see it has to be true. To generalise it, so if K or more objects are going to be placed into n holes, then at least one hole must contain that expression there, which I'll explain in a second, or more objects. Now, I don't know whether you would have seen this notation before or not. It's what's called the ceiling function. So it's a bracket, but with the bottom cut off. So it just has the top of the bracket and the line down. That's called the ceiling function. And there's the definition of the ceiling function. If the ceiling function of x is equal to y, then x must be greater than y minus 1, but also less than or equal to y. It must be somewhere in between. That's what it's basically saying. In other words, it forces you to always round up regardless, so you never round down the number, which is why it's called a ceiling function, because you always round up. There is also another thing known as a floor function, and the symbol is very similar, except now the top bracket's cut off as the bottom one's there. But we don't use that one. We use the ceiling function for this. Integers are going to be selected from this set of numbers. All the integers going from 3 to 12. What's the least number of integers we need to ensure that we get a pair of numbers that add up to 15? So we're just going to randomly pick numbers. How many numbers do we need to ensure that we've got 2 numbers that will add up to 15 in our collection of numbers? There are 5 possible pairings out of all of these numbers. And here they are. 3 and 12, 4 and 11, 5 and 10, 6 and 9, 7 and 8. So the way we could think about this is we're going to pull numbers out of our set and place them in the appropriate subset. So if I pull out 3, I'll put it in the first one. If I pull out 5, I'll put it in the third one. So they're, if you like, the pigeonholes. They're what we're going to put them into. So 5, n is 5. So the principle tells us that 6 integers need to be selected then. We need one more than the number of holes. So if I pull 6 numbers out, I must get a pair of numbers that add up to 15. Now, how could I use the ceiling function to do that? Well, I'd say, well, it's the ceiling function of k, because that's what I'm trying to work out. How many objects do I need? Over 5, that was the number of holes, and the answer to that has to equal 2. So k over 5 must be in between 1 and 2, but not including 1. Multiply by 5, k needs to be between 5 and 10. We want the smallest number that satisfies that, so 6 would be the answer. Now, I probably wouldn't use the ceiling function for that because I think that's fairly quick to come up with the answer just looking at it logically. We've got 50 points and we're going to place them in a 7 by 7 square. What's the maximum distance apart that the 2 closest points could be? So you're randomly placing these 50 points. We want the 2 closest points in that, and we want to know what's the greatest distance they could be apart. So what we do is we look at this square, but think of it as 49 1 by 1 squares. So we've got 49 1 by 1 squares, which is nice because it's 50 points that we want to place, you see. So 49 1 by 1 squares. they will become the holes, the 49 1x1 squares. We're going to place 50 points in these squares. So it should be possible to do it where at least 2 points will be in the same square. So they're the objects. All right, so let's now think of that 1x1 square where we've placed 2 points. They have to be the two closest points when you think about it. Where would you place them in a 1x1 square so that they're the greatest distance apart? Right, either end of the diagonal. Therefore, a bit of Pythagoras, and we work out the square root of 2 would be the greatest distance 2 points could be. We've got a group of n people. And we're going to prove that in this group of n people, there will always be at least 2 people that have the same number of friends in that group. There always has to be 2 people with the same number of friends. Okay, let's think about this logically. It's not going to be possible for one person to have no friends and another person to have n-1 friends. That would be impossible. Okay? Because if someone had n-1 friends, then they must be friends with every other person in the group. So then it would be impossible for someone to have no friends because they're friends with that person that has n-1. So it's either 0 friends we discount or n-1 friends. We know one of those possibilities can't happen. I'm discounting the no friends because everyone's got a friend, surely, you can't. The possible number of friends they could have would be then 1, 2, 3, up to n-1. So there's n-1 different number of friends a person could have. But there's n people. Right? So the number of friends will be like our pigeonholes. We can grab the person and say, well, how many friends have you got? Oh, 5. You go in the pigeonhole that has 5. How many friends have you got? Oh, 7. You go in the pigeonhole that has 7 friends, and so on. We could go along every person. But we'd have to place all of those people. We've got to place n people in n-1 holes. So there must be one of them that has at least 2. Therefore, there must be 2 people with the same number of friends by our pigeonhole principle. Oh, this is a good one. 16 positive integers are written on the board, totally random. You can pick any integer you like. At least how many numbers will have the same remainder when we divide by 5? There are going to be 5 possible remainders. 0, 1, 2, 3 or 4 when we divide by 5. So they are the holes, if you like. Whatever number you write on the board, we'll place it in the appropriate remainder hole. We are placing 16 objects into those 5 holes because you're going to put 16 numbers on the board. Well, this is where the ceiling function will come in handy, because I can work it straight out. Ceiling function of 16 on 5 is the ceiling function of 3.2. Well, you always round up in a ceiling function, so there must be at least 4 numbers that will have the same remainder. Next example. This one's really good. We've got a computer, and it's going to generate 3-letter words. And by 3-letter words, we just mean an arrangement of 3 letters. Could be anything. How many words do we need to generate to ensure that there is a word on our list that has been generated 8 times? How many do we need? So how many words are possible? Well, 26 times 26 times 26. We've got 17,576. There's our pigeonholes, because the word's going to come up and we'll go, right, we've got that word, in that hole it goes. And so on, and so on, and so on. So we have 17,576 pigeonholes. Let's use the ceiling function for this one. K, that's what we're trying to find out. How many words are we going to do? So the ceiling function of K on 17,576, the answer to this must be 8. Therefore, K over 17,576 must be between 7 and 8, not including 7. Multiply by the denominator, and we can now easily see, we need 123,033 words to be generated, and no, we're not going to test that one out. All right. We'd be here for a while, that's for sure. All right. So that's the idea of the pigeonhole principle. So exercise 14H.